summarize what we were talking about last time. We were talking about center of mass. Center of mass. And so for a mass distribution or a bunch of the center of mass for a collection of different masses. So actually, why am I writing M? So yeah, actually M. So the total mass, if I have a bunch of different masses, looks like this. So this is the total mass. Total mass. And the position of the center of mass, we wrote as 1 over m, so it's weighted by the mass. The sum over the positions of each one times their masses. And I don't need to divide by anything there. So I could have just written it like this. X, I, M, I. And these are vectors, and so this is a vector. So that's what we talked about last time. So now what we're going to do, and as an example, we also introduced this idea of superposition, where you can add the center masses of if you have the example we had of a piece of an object. The example we had last time is if we had a disk with a hole in it. It's easy for us to compute the center of mass of things with a lot of symmetry. So a disk, this filled in part, we knew this. If this were filled in, we would know the center of mass is in the center. If this whole thing is filled in, we know the center of mass is here. And so we can compute the center of mass of this disk with the hole in it by using the fact that we know the center of mass of this round thing and the center of mass of this round thing and combining them in superposition. So this is like kind of a theme. If you know that if you have a symmetric object, you use the fact that it's symmetric to help you do calculations. So that was the example we did last time. So I have one more example to talk about, and that was, these are vibrational motors. So we have a lot of fun with vibrational motors in the lab because they're really cheap and small. You can play around with them. But, and they're easy to power. All you need is 3 volts or 4 volts or 5 volts. DC power, nothing fancy. So a coin vibrational motor, what's a coin vibrational motor? So I don't know how many of you guys have played with these things, but they tend to be, so the common type is, it's centimeter, actually not in radius, in diameter. They tend to be a centimeter in diameter about, although you can get smaller ones. And this is maybe a millimeter or so, 1 millimeter. And they're in the shape of a disc. And then there's 2 wires coming out. And you plug them into 3 volts, typically DC. It doesn't even matter which way you plug them in, it will still, and then they start to vibrate. So what's inside a vibrational motor? So if you open up this thing, and they're pretty easy to take apart. What's inside is a flywheel. So, and it's lopsided, so they look something like this. And this thing has it has a circuit on it that makes the motor, that helps the motor turn. But the flywheel here is lopsided, so there's more mass on this side and that side. And so when this thing spins, the center of mass is around here. The center of mass is actually moving with respect to the case. And so if you let the whole thing balance around the center of mass, it would balance here. And that means the case would swing around. Or it doesn't actually rotate, the case moves so the case moves like this around the center of mass position, which is around here. And if this thing is inside your cell phone, the whole thing feels like it's vibrating. Well, why does it feel like it's vibrating? Well, it turns out your hands are very sensitive to vibrations at a couple hundred hertz. And so they typically are around 200 or 300 hertz in their frequencies of oscillation, and equivalently 9,000 RPM or so. And this just so happens your fingers are really sensitive to vibrations at that frequency. And so if your cell phone is vibrating on that, you notice it because it's just like a little buzz. So these things, they're pulsed. So they're not meant to be run for a long period of time. They're pulsed to make you notice, your fingers notice. So this is in the setting of haptic, what's called haptic haptic feedback, where you try and get computer equipment or just, you know, handheld, anything that you use to give you these little pulses that your fingers will pick up on. And so haptic has to do with this idea of touch. So yeah, so these things are now actually almost in a lot of common handheld equipment, things, not just discs. So these are coin vibrational motors, but there's also cylindrical ones. So when I say they're pulse, they're not very efficient, and they dissipate quite a bit of energy, but they're not supposed to be turned on for very long. So if you use them for, say, making things move, so we were playing around with them just in the lab to see if we could make little clever mechanisms with them, because they're cheap. They only cost a couple dollars, and they're really easy to power. But if you turn them on for a really long time, or you hold them and don't let them move, they tend to burn out. They're pretty enclosed. You can get them wet and they won't die. So they're kind of fun to play with. In any case, they work because the center of mass is not the center of mass of the case. The center of mass is slightly off, and they're designed to run at this pretty high frequency, so that your hands feel them. So on the theme of center of mass. Okay, so now we're going to move on and talk about multi-particle systems. So when we have center mass, we can think about rigid bodies, and we can think about multi-particle systems. So our thing we're going to talk about now, multiple particle systems. So each particle could be moving together, and that would be a rigid body. Or they could be moving individually. So that would be like a gas, or, you know, an asteroid belt, something like that. So, so the velocity of the center mass, we have an expression for that, with just like the position of center mass looks like this, mvi. So these are the masses, and this is the total mass. So this is for n particles with mass mi. And these can be vectors. So the total momentum so if it's we can write that as just a sum of the individual momentum. And if it's not relativistic, this is MIVI. And if it's relativistic, so this is non-relativistic. If it's relativistic, we can generalize this gamma I V I. So where gamma is the Lorentz factor, which depends on the velocities. So it's pretty easy to come up with a generalization for total momentum that's correct for relativistic setting. So now what if we have internal forces? Okay, so let's assume that we have internal forces. So what do I mean by internal forces? So internal forces, I mean among the particles. So I have n particles. They're influencing each other. So there's forces between particles. So this is the same thing as forces between pairs of particles. So supposing I have a particle from particle J onto particle I, then that would change the momentum of particle I. But I know from Newton's laws that has to be, so this is forces between particle I and J. That has to be the opposite of the force on particle J. And that means the change in momentum on particle I has to be the opposite of the change in momentum on particle J during a small period of time, dt. So since that's true, we can, it's the same thing as saying this, but this is true during every time step or every small period of time. So what happens to the total momentum during any length of time? If for every little drop of momentum on one particle, I get it back on the other one. And so the total sum stays constant. So as long as you have internal forces, the total momentum P is conserved. It stays the same. So with internal forces, the total momentum P, which is the sum of all the momentum, is conserved. And that's the same thing as saying is constant. So an example might be an n-body simulation where I have all masses interacting with each other gravitationally. But if I add up the total momentum, it'll be constant. It should never change. So it's a conserved quantity. Another example would be a bunch of electrons in a plasma, electrons and nuclei ions. So a plasma, these are a bunch of particles that interact electromagnetically with each other. Again, the total momentum should stay fixed because all of the interactions are within on each particle on each other, and they're always symmetrical, equal, and opposite. And so the total momentum stays fixed. So that's when you have internal forces. So sometimes we could also say, yeah, so what if we have our plasma, but it's also feeling a gravitational force that's coming from somewhere else, from a big planet, a mass that's distant. Or we're on the surface of the Earth, you can think of the gravitational acceleration as something that's distant, but the particles could still be interacting or, so you can think of that as an external force. So what happens when we have an external force? So things are a little bit more interesting when you have external forces. So, right, so external forces. So we could have a change in momentum, which is now the sum for all particles, the change of momentum. And the momentum now is, the total momentum is not necessarily conserved because, think about gravity, we're exerting a force on all the particles at once. There'll be a work done on every particle. And so total momentum will change. Or you can just say, well, let's think of dropping a whole bunch of particles all at once. The gravity is letting them all fall. The kinetic energy of all of them is increasing. So the total momentum is going to change. So we could compute the change in the velocity of the center of mass of the system. So we have all these particles, we can always compute their center of mass velocity. So I can always compute, so for non-relativistic setting, I can always compute the change in the center of mass velocity just by adding up the sum of the changes in the velocities. So I could always do that. And the change in the total momentum is just mass times dV, m times dV for non-relativistic particles. And I can always compute a work. So this is the change in the total momentum. And this is equivalent to sum over I m I dV, right? You can see these things. This turns right into that just by multiplying by m. I can also compute work on the entire system. So this is now a sum over the force times distances for each particle. And that is the sum of the changes in momentum. So if over a small length of time, it's this, so the force turns into the sum this is over a small period of time, so you could integrate that up. And this is dxi like that. So, so what we're going to do later is we're going to look at the work done on the center of mass, and then we're as a separate thing, and we're going to find out that it depends on the sum of the forces on every particle. And for some forces, that's really easy to evaluate, particularly position-independent forces. That would be easy to evaluate. But when you think about the total energy change on so the work, this is essentially the total energy change on the whole system done by this external force. Sometimes it's nice to think about that as a work done on the center of mass plus an internal work done with respect to the center of mass. So there are problems like gravity where you talk about the gravitational force on the center of mass plus like a tidal force, which talks about deformation caused by gravity. And that's an example where you would take the energy input or the work and divide it into these two different settings, the work on the center of mass and the work done on the internal for degrees of freedom of a body. So we're going to do that a lot, where we talk about energy and how we divide it up into different ways. So before we do that with work, what I'm going to do now is talk about kinetic energy. So we'll take kinetic energy, and we'll divide kinetic energy into two pieces: the kinetic energy of the center of mass and the kinetic energy with respect to the center of mass, so the velocity differences. And so for many of our problems, you can describe the motion as a drift in the center of mass plus internal oscillate, say. So for example, a spring system of two bodies, you can describe that problem as a center of mass drift plus oscillations in the two bodies. So that's a molecule. Or a rotating molecule, that's a spin degree of freedom plus a drift in the center of mass. So there's a lot of problems where we take kinetic energy, we divide it up into these two pieces. So let's do that. So kinetic, so what am I talking about? I'm talking about kinetic energy of a multiparticle system. So let's just write down what we expect it to be. So this is for n particles. The total kinetic energy is just the sum of mv squared. So this is non-relativistic. Okay. So what I'm going to do now is add and subtract some things. So let's add and subtract some terms here. So I'm going to keep this. Don't forget this one. Mi vi squared. I'm going to add in, so let's subtract 2 mi vi dot v center mass. And now I'm going to subtract it out. So I've subtracted it. These are vectors. Now I'm going to add it. And this is a sum. This part is the sum here. I probably should write the sum. Let's make it clear that there's a sum. Like that. And there's a 2 like that. And now I have to add, since I subtracted it, I'm going to add it back. I vi dot v center mass, like that. Okay, so that's one set of terms. Now I'm going to also add and subtract 2 more terms. Vi squared, and not v center mass squared, minus sum of the mi v center mass squared, like that. So added in, subtracted this, added it in, so they cancel, added this, subtracted this, so they cancel. Okay, so now a matter of regrouping terms. So this and that, I could put all together as a single term. And so let's write it out that way. Sum of mi vi minus v center mass squared. So you can see this if it's vi squared is that term minus 2 v center mass times vi is that term, and then I have a v center mass squared, which is this term. So then what's left over? Left over is 2 mi, that's this one, vi v center mass with the sum, and then this term minus sum mi v center mass squared. So this, right, that's good. So this, this here is the sum over mass, so I can replace this with m. Get rid of the sum. And yeah, and this is actually it's actually m times v center mass. So I can replace this with m times v center mass. And this is now a dot product. And that's the same thing as v center mass squared. So I can replace that with this. And now this is the same as that. This 2mv center mass squared minus mv center mass squared. So I can subtract this one off of this one. And I get this. So this is what I wanted. And so now what we can do is look at this formula. So, so let's take the 1/2 and multiply it both out, 1/2 here and 1/2 there. So this you can recognize as the kinetic energy of the center of mass. So it's mv squared, where that's the velocity of the center of mass. So this is the kinetic energy of the center of mass. Sometimes we call this the translational kinetic energy. It's the whole system as if it was one mass, all drifting together. What's that? Center of mass. This, so vi minus v center mass is the velocity of this with respect to the center of mass. So think about that, like if we had a spring system, each particle is moving with respect to all the others. So this is the kinetic energy. This is like internal kinetic energy, and that would include vibrational motions. It would also include rotation. So if you think of a wheel rotating, you have the center mass of the wheel moving, but then you have all the particles moving with respect to the center mass, and they're rotating around it. So this would include rotational and vibrational degrees of freedom. So we can talk about this as like a relative. So this is a relative or internal relative kinetic energy plus translational kinetic energy. And you could always take the kinetic energy and you could always divide it up this way, where it's the total plus an internal bit, where you have velocities with respect to the center of mass. So, right, so now let's do this for a 2-particle system. So 2-particle systems are particularly nice because they have this nice form for the internal degrees of freedom. So I'm going to talk about the kinetic energy of a 2-particle system. So, so we have V1 and V2 and M1 and M2. So those are the velocities of of each particle. They're their masses. So it's convenient to define a velocity. So V1 minus v center mass. Okay, so this is the velocity of the first particle with respect to the center mass, and u2 is v2 minus v center mass. And again, these can all be vectors like that. So it's convenient to do that. So in the center mass frame, so if I subtract off the center of mass, it's like going into a special frame, center mass frame, where all velocities are measured with respect to the center of mass. So in the center of mass frame, we moved so that we're moving with the center of mass. So the center of mass has 0 velocity. And in that frame, this is true. So if I compute the center of mass velocity in the center of mass frame, I get 0. So this is equivalent to computing the center of mass velocity. But because I'm using velocities with respect to the center of mass, they add to 0. So these are, so U1, let's be specific, U2 are velocities with respect to the center of mass. And we could show that this is true by using the definition of the center of mass velocity. So the v center of mass is m1 v1 plus m2 v2 divided by the total mass. So this is what our definition was for the center of mass velocity. Okay, so starting with this equation, it's handy to, once again, add and subtract some things. So I'm going to minus m1u2 plus m1u2. I'm going to add those two terms. So this is a cross term, m1u2. And then, so I'm subtracting it and then adding it. So using that, I can now write m1 u1 minus u2 plus m1 plus m2 times u2 is equal to 0. And so that gives me u2 is equal to m1 over m1 plus m2 times u1 minus u2. And there's probably a minus sign. Yes, there is. Okay, so what did I do here? I came up with a formula for u2 in terms of the velocity difference. So that's convenient. And I could do the same thing. Instead of adding and subtracting m1u2, I could do m2u1. And I could come up with an equivalent formula that's u1 in terms of the velocity difference. And it looks like this. So the velocity difference is this nice thing. So let's define it. U diff is u1 minus u2. And because u1 is with respect to the center of mass, this velocity difference is the same thing as v1 minus v2, actually. It doesn't really matter because both of them, if you subtract out the center of mass, add and subtract the center of mass, you get the same thing. So this is a velocity difference. So that's convenient. So now let's, taking these definitions, let's now rewrite the kinetic energy, not in terms of the original velocities, v1 and v2, but in terms of, we're going to try and write the kinetic energy in terms of velocity difference and the center of mass motion. So let's do that. So K, so let's do this in the center of mass frame. m1u1 squared plus m2u2 squared. So this is the kinetic energy in the center mass frame. So I'm just going to now put in our formulas that we had calculated from the velocity differences, and this is m2 over m1 plus m2, and that's squared times the velocity difference squared, u diff squared, and then we have a similar term, m2 times m1 over m1 plus m2 squared times the velocity difference squared, like that. Okay, so that's it. So now we manipulate some terms, and when you go through and cancel out everything, you can rewrite this to look like this. M1, M2 over M1 plus M2 U diff squared. So I'm not doing all the terms, but if you do actually evaluate all this, this is what you get. So this thing, so it's a product of M1, M2 times divided by the sum. This thing has a special name. It's called the reduced mass. So we can rewrite this, and often it's given this symbol mu. So I can write it like this. So it's the reduced mass times U diff squared. So the kinetic energy in the center mass frame, so we went and got rid of the center mass motion, can be written as if it's a reduced mass times the velocity difference squared. So, so that's a really handy formula to use for two-body problems. So now let's go back into the actual frame. This is the kinetic energy in the center mass frame. So let's be specific. It's the kinetic energy in the center mass frame. So now I can restore the center mass, the kinetic energy in the lab frame where we could have some center mass motion would look like this. U diff squared plus 1/2 m v center mass squared. So this is the total mass times the center mass. And this follows from what we had done before, where we said you could always write the kinetic energy as a sum of the center mass motion plus the sums of motions with respect to the center mass. And this thing, you could always write this out as if it's the motions with respect to the center mass. We showed that here. So this is equivalent. So yeah, so this is a handy formula, and now I'll show you how we can use that to make some problems simpler. So there's two settings where it's really useful. One is like these like molecule setting. You have two atoms in a molecule. Supposing they're having vibrations, then you can figure out what the frequency is of the vibrations, not using the mass of one of them, but the reduced mass. So you get, if you have a molecule, it looks like this, M1, M2 with a spring in it, the frequency of motion is the square root of k over mu instead of the square root of k over m. And that's coming from this, because it acts like it has this other mass in the center mass frame. Okay, so let's do the two-body problem. The two-body problem. So the two-body problem is, we mean gravity. So it's two masses plus gravity. So it's convenient. So before I do this, is two masses. Well, let me first explain what we mean. It's two masses plus gravity, the gravity force. And not gravitational acceleration on Earth, but actually gravitational interaction. So what did I call the masses? M1, M2. So it's M1, M2. And the gravity force, remember, looks like G, M1, M2 divided by R1 minus R2, where these are position vectors. Oops, so this is squared, and then it's R1 minus R2 hats. This is let's be specific. R1, 2 hat. That's the unit vector that's pointing in between them. And you can see I was writing out the potential energy. Potential energy looks like this. Yeah, much easier to write out the potential energy than the force. Okay, so let's write down the total energy for the two body problem. So it's the sum of the kinetic energy plus the potential energy. So this I already wrote down the potential energy. That's it, and you can see it depends on the position difference. So this is it's a vector between the two particles. So last time when we were talking about the kinetic energy for a two-particle system, we wrote things out in terms of the velocity difference. So this is the vector between the two masses. And so you're starting to see where we're headed, is that we're going to show that the energy looks like the center of mass drifting along, plus another two-body problem in terms of the relative both position and velocity. So that's where we're headed. So before I do that, I want to write down one formula that's useful, and that's M1, M2, which is here, is the same thing as mu times m. So let's check that that's true. So mu is the reduced mass, which is m1, m2 divided by m1 plus m2, and m, which is the total mass, is m1 plus m2. So these cancel, and then you see that it's the same thing. So, so that showed that this was in fact true. So this is useful for looking at the potential energy. So let's write down the total energy. Total energy, E, it's going to be the kinetic energy plus the potential energy. And the kinetic energy I can write as a sum of the center of mass part plus the relative part. So the kinetic energy looks like this. U diff squared plus 1/2 mv center mass squared. And let's call this R diff. I'm going to define actually I could give it a vector. It doesn't have to be a length. And now I need to add in the potential energy minus G, which looks like this, but I can rewrite M1, M2 as this. G U M over R diff squared, like that. So that's the total energy. So let's look at this again. So we have the center of mass motion, which is kind of by itself. And then we have a kinetic energy that depends on the velocity difference, and a potential energy that depends on the distance between the, this is just a radius, between the two masses. So this problem looks just like a single mass, a very low mass in orbit around a really large mass. And so you look at it, so this is the potential energy for a really small thing in orbit around the sun or something like that, where the total mass of the body that it's in orbit around is this big M. And this is the kinetic energy of that small thing. So the two-body problem, where you have two masses, we didn't say anything about one of them being big or small. You can rewrite it as if it's a massless particle in orbit around a large mass. So the mass of the low mass particle has the reduced mass, and the mass of the big thing, and for the analogy, is the sum. So if you can solve the problem, solve the Keplerian problem for a low mass particle in orbit around something really big, you could also solve the two-body problem for any mass ratio. So that's the point here. And the center of mass is essentially unaffected. It just drifts along forever. So we only wrote this out as an energy, but you can do the same thing with forces. So you can write down the equations of motion and show that you can solve the problem of the velocity of the relative coordinate separately from the center of mass motion for the two-body problem. So that's kind of the point. So yeah, so did most of the examples here with velocities with respect to the center of mass in the non-relativistic setting. In the relativistic setting, you can also find a center of mass frame. So it's the center of momentum frame where you have the sum of all the momentums are 0. So instead of looking for, instead of weighting velocities, you weight momenta by the, you sum up all the, so you try and find a Lorentz transformation such that the total momentum is 0 for all your particles. So, so there's definitely an analogy for relativistic groups of relativistic particles. It's a little bit harder to calculate because you're searching for the frame that gives you, it involves those Lorentz factors. So it's a little bit harder to find the frame, but it definitely exists. Okay, so let's do an example now. An example. So the breakup of a projectile. So that's the example. So, so what do I mean by that? So I have like some rocket fires or goes up in the air, and then it's a projectile. So it would have been on some parabola. So this is gravity. So there's G is the gravitational force down. But in the middle of this trajectory, it breaks into two pieces. So one piece goes this way, say. So here it breaks into half, and the other piece goes here. So we have a breakup. So when it breaks up, the two pieces could push against each other. I mean, there may be an explosion. You can even have an explosion here. And so what we're going to show is that the center of mass of these two particles is going to stay on the original trajectory. So if you see, and yeah, so that's basically what we're going to show. Center of mass will drift as if it were under gravity alone, all by itself. And in fact, if you were missing a piece, you could figure out from looking at one of them, you could maybe guess where the other one is from knowing the original trajectory. So, so that's what we're going to find out. So in some sense, so we know when it breaks up, that's internal forces. This system is under this external force, this gravity force pulling it down. But when it breaks up, the total momentum at the moment of breakup isn't changed. And so the momentum is only, the total momentum of all the pieces is only affected by gravity and nothing else. So at this moment, there's no change to the total momentum because only internal forces cause the breakup. So, so let's write the center of mass velocity is 1 over m times the sum of all the sum of m I v I, like that. And we can compute the change, the acceleration on the center of mass just by taking the derivative of this thing, m I d v I dt. And since the only force on this problem is gravity, this is the gravitational acceleration. So this is acceleration of the center of mass. And I could write this out as 1 over m times the sum of m I times g with a minus sign. And we know which direction it is. It's got a minus sign here. It's down. And this is a constant. So I have the sum of m, this is the same thing as that. So I can rewrite this as minus gz hat. So, so this shows you that the acceleration on the center of mass is the same thing before and after the projectile breaks up. So yeah, so we can predict it at all times. It doesn't matter about the breakup. The breakup didn't affect it. And the reason the breakup didn't affect it is because that didn't change the momentum of the combined system, the total system. Because whatever change in momentum went on this one also went equally and oppositely onto the other piece. So that's kind of the point. Okay, so that was one example. Let's do another example. Breakup of a projectile. Let's do a jumper. Mass spring jumper. So what do I mean by mass spring jumper? So I have a mass M2 here, and it's connected by a spring with spring constant K to another mass M1, and they're sitting on a tabletop. And the first question I want to ask is, if I push this down, I'm going to push it down by a certain distance. How much am I pushing it down by D? I'm going to push this down by a distance D. So if the spring is strong and you push it down a lot and then you let it go, the M2 will start to spring up. And if the spring is strong enough, the whole thing will then come off, both masses will jump off the table. And so the question is, what condition allows this thing to jump off the table? So you could think of this as a little a little actuated thing where it pulls down, and then how far do you need to pull down that spring for the whole thing to then jump off the table? So that's why I call this a jumper, because you can get it to jump off the table. And so if you think it's hard to get things to jump off surfaces on Earth, it's very much easier in space. So a jumping locomotion mechanism on an asteroid, for example, is actually pretty easy. You don't think that's because gravity is a lot less. So we'll try and answer that. So what condition allows both M1 and M2 to be off the table? So that's the first question I'm going to ask. Then the next question is, well, what happens to the system after it's off the table? So while M1 is on the table, we can think of this problem as M2 connected to a spring to a fixed point. So M1 is sitting there, it's not involved, it's not moving. So you can just think of M2 oscillating up and down on a fixed point. But when M1 leaves, now we have a two-body system, like a molecule connected by a spring. And so the equations of motion are now like what we had before, when we were talking about dividing kinetic energy into relative motion and the center of mass motion. And so this mass spring system now, once it's off the table, we can predict what it's doing by having the internal motion of the mass spring system plus the center of mass under the action of gravity, and that's it. So solving the problem is now two simple problems: gravity on the center of mass and the oscillation of like a molecule. So that's the second question: is find the equations of motion after it leaves the table. So, and we'll show that that's what you get, the center of mass plus gravity with gravity on it, and an oscillator with that frequency is the reduced mass. Okay, so those are what we're gonna do. So let's now do this. Okay, so since M1 is on the surface of the table, we don't have to worry about its motion. I guess there's one more piece of information, and that's the rest length of the spring has a length L. So the equation of motion for Z2, so Z2 is the position of M2. Z2 is position of M2, okay? And so this is the mass times acceleration. This is a double dot, so Z, I've written down shorthand d squared Z2 dt squared. So that's the acceleration of V2. And now I need to give it the spring force, Z2 minus L. So this depends on the rest length. So if Z2 is bigger than L, then it pulls. If it's less than L, then it pushes. And I also have gravity. And that's a minus sign because I'll take Z2 as the position of M2 in the vertical direction. So it's the upward direction. So that's the equation of motion of Z2. Good. So what's in the solution to this? So the solution to this looks like this. Yeah, L minus M2G over K. So that gives me a rest thing. So I canceled this out with some rest displacement. And then I could also have an oscillating term in there. And I'm going to label it by how far the spring is initially compressed. Cosine square root of K over M2 times T, like that. And this is the frequency. So this is the frequency of the system if only M2 is allowed to move, M1 doesn't move. And so this comes from the initial condition where we compress the spring by an amount D. Okay, so that's the solution to this. And so now once I have the solution to this, I can compute, I know what I know what Z2 is at all times. So, but this is the spring force. Spring force. And there's an equal and opposite force on M1. And so the question I can ask, so if I put this solution here and then compute the spring force, I can ask, when does the spring force exceed gravity on M1? And so that's what I'm going to do is put the solution, compute the spring force, and see when it exceeds gravity. And when it does that, that means M1 can leave the surface of the table. So let's do that. So right. Yeah, so the equation, so let's write down the equation for M1. M1, if we didn't have the tabletop on it, M1 would look like this. So without the table, the equation of motion of M1 looks like this. Z1 minus Z2 minus Z1 minus L, like that. That's right, minus M1G, because it's also feeling gravity down. And so now we'll put this solution in there. And if you put that in there and evaluate the terms, you get this. G minus KD cosine square root of K over 2T, like that. So when this thing is greater than 0, then it leaves the tabletop. And so that actually now gives you a solution for what D is in order to, well, so this, I guess this thing is the question is what the condition is that will let it leave. Well, the cosine is at maximum a value of 1 anywhere in the motion, so you set this to be 1. And the condition that it can leave the tabletop is this. 2, that's a 2. G. And that's the condition. And so essentially, what does this condition mean? This means that the force in the spring exceeds the force in gravity from the total mass, exceeds the force on the total mass. So it makes sense that this is the condition for what you would need to put, how far you need to push it down, and how strong a spring you'd need in order to let the whole system come off the table. So we answered our first question. So now let's talk about the behavior of the system after it's off the table. So now we just have a mass, 2 masses with a spring moving through free space. So there's no connection to the tabletop. So I'm going to write down the equations of motion. So we remove the table essentially now. So I'm going to write down the equations of motion for both masses. Minus M1G minus K, and this is Z1 minus Z2 minus L. So that's the equation. So this is the mass times the acceleration on the first mass. It's feeling gravity and it feels the spring constant. The equation of motion for the second one looks like this. Minus K, we have to flip some signs here, or I can just flip it because it's equal and opposite, like that. So those are the equations of motion for each mass, and they depend on the distance between Z1 and Z2 here. So let's manipulate this. The easiest thing is to add them and then subtract them. So let's subtract. So I'm going to subtract this one from that one. So is that what I want to do? Yeah. So it's actually easier before I subtract them. So I want to subtract them so these things go away. So before we subtract them, let's multiply. So M2 M1 Z1 dot is equal to minus M2 M1. I'm multiplying this one by M2. So, and I'm going to multiply this one by M1 minus M1 M2G plus K M2 Z1 minus Z2 minus L, like that. And now I'm going to subtract them, and I'll get M1 M2 Z2 minus Z1. So I'm subtracting this one from this one is equal to, these two terms go away, and I get minus K, and you can rewrite, this is K M1, K M2, we can, when we subtract this, it's going to be, right, we have a term for each one, M1 plus M2 times Z2 minus Z1 minus L, okay? So let's now rewrite this in terms of a difference between, so we'll take Z diff, M1, M2, Z diff, double dot equals minus K, M1 plus M2, Z diff, minus L, I guess I can do that if I want. And we can divide this on this side if you want. M1, M2. And you can see that we could rewrite this as, or let's move this onto the other side actually. let's leave it over here, m1, m2 over m1 plus m2. You can rewrite this as z diff double dot is equal to minus k z diff. And sometimes it's convenient to define this as the difference from the rest position. So let's just rewrite it like that. Diff, and we'll define z diff as z2 minus z1 minus that, like that. And what do we have? This. This is an equation of motion for the difference between the positions, and it looks just like the harmonic oscillator, except the mass is the reduced mass. The spring constant is still the same. And so this is consistent with what we had before, where we talked about molecule. What is the frequency of vibration? The frequency of vibration is the square root of k over mu, where mu is the reduced mass of the two mass system. So that's what you get when you subtract these two equations of motion. What happens when you add these two equations of motion? So let's do that part now. Yeah, okay, so that's this. So let's add these two equations of motion. M1 Z1 double dot plus M2 Z2 double dot is equal to minus M1 plus M2 times G. This and that cancel. And we can rewrite this as MC center of mass double dot equals M1 is equal to MG, like that. Where Z, center of mass, is what you expect over M1 plus M2. Okay, so this is the equation of motion of a single mass only feeling gravity. Okay, so let's summarize what we did. We subtracted these two equations, but in such a way that we could cancel out the gravity. And we showed that you get something that looks like a mass in a spring, except that the mass is now the reduced mass. And the coordinate that describes it is the difference between the distance of the masses. Then we added these two, and we got the equation of motion for the center of mass feeling gravity and nothing else. And so the spring completely dropped out of the problem. So this is actually much easier to solve now. We can just think of it as two bodies, center mass system drifting, but only feeling, it's not drifting because it's feeling gravity, but it's under gravity. And then the harmonic oscillator is a separate problem. So you can ask, well, how do we solve this? We could start off, I could ask, well, if I want to solve it after it leaves the tabletop, all I need to do is find the initial conditions. So that means what's the velocity of M1? And so I know the velocity of M1 when it just leaves the tabletop is 0. What's the velocity of M2 when M1 is about to leave the table? So we could solve for that. Then that would give us the center of mass velocity at that moment. We could also solve for the position of the position difference at that moment. And then we can solve for the velocity difference at that moment. And so those are all the conditions you need, but now they're in terms of the center of mass, position and velocity, and the difference position and velocity. Solve the two problems separately with their initial conditions. And then if we want to, we can go back and get the full solution for where is M1 and M2 at all times afterwards. So the problem is like now tractable. We can predict what it's going to do at later times. So I'll stop there. Does anybody have any questions about this example?
Professor, I have a question.
Yes.
What exactly does the add and subtract apply?
So I did that as earlier I showed you that you could take the energy and you could divide it in these ways. For this problem, I showed you that we could take all the force equations and do the same thing and show that you could decouple the problem in terms of a center of mass and a internal problem. So that's kind of what so I did it very specifically with the equations of the motion. And these are the equations of motion for the two system. If you add them together, you get the equation of motion for the center of mass. If you subtract them, you get the equation of motion for the internal degrees of freedom. So you could write, like, what if I had 10 particles all connected by springs and gravity? You could do the same thing. So you get this big matrix equation, and you can solve that. So that's something that you will do later on in the term, is instead of just having a single distance, you'll have more degrees of freedom if you have 5 springs and 5 particles, or maybe 6 springs. So you would get this, the force, would then be a matrix here. And you think of this as a matrix times a vector of positions. So you can see the hint of how you would generalize this for a more complicated system. I'm not sure if that answered your question. So all I did was show you that you could get what we were expecting from our energy discussion, that we could divide it into these 2 pieces, or into 2 separate problems. I mean, if I had a lot of masses and springs, I could always add them all up and cancel all the spring forces and get the gravity term separate onto the center of mass. So any mass spring system thrown into the air will act like it's moving, or it's feeling gravity on its center of mass, actually. And then all the internal degrees of freedom and oscillation, you can solve that problem entirely separately. Does that kind of answer your question?
Yeah, thank
Okay.
you.
More questions about working with the center of mass for multiparticle systems? Trying to figure out what are we doing next. Oh, we're going to talk about thrust. Okay, good. So we still have some time. So let's talk about the next example I want to give is a conveyor belt. This is a cute example. So, yeah, it's time to draw this picture. Okay, cool. So the picture is, we have, yeah, so here's a wheel, and here's another wheel, and there's lots of colors here. Okay, so there's a conveyor belt that goes around this wheel like this. So this is not a good one. Here's a good one. That is a conveyor belt. And we have a hopper. Let's put the hopper in. Here's the hopper. This is a hopper. My artwork is not so good. So out of this hopper, we have something on maybe sand or something. Grain. How about grain? Like seeds or something. And out of this hopper is coming some grain, and it's flowing on the conveyor belt. And then it's falling off into some bin over here. So making a pile. Let's make a pile. Okay, so this is grain. Great. So the question is, and we need some physical parameters. So we have the mass flow rate of the grain. So let's call this R is equal to dm dt. This is how much mass is coming out of the hopper. And we have a velocity for the conveyor belt, v. So that's the speed of the conveyor belt. So what's the question? The question is, how much force do you need on the conveyor belt to keep it moving at that velocity v? So because the mass is coming out of the hopper, as soon as it hits the conveyor belt, it has to be sped up to this velocity v. So the conveyor belt actually has to push on, it has to accelerate the grain to get to the velocity v. So the question is, what force what force F is required to keep the belt at velocity V. So that's the question. So, right. So the mass coming in, we have dm dt coming in is this R, the rate, it's a mass rate, is the same as it's coming out. So dm dt is dm dt in is this dm dt out is R. And so what's the change in momentum dp of a small bit of mass? So this is the change in momentum. So dp is equal to dm times v, because I need to accelerate it to this velocity v. So delta v is v because it starts from rest. So that means dp dt is equal to dm dt times v, which is equal to rv, because r is our mass rate. So the force required is rv. That's basically it. That's the answer. The total momentum of the system is in steady state at all period of time, but we keep putting in the same amount and taking out the same amount. And when we put it in, we're speeding it up by an amount that's the force that we need is this. So that's the answer. It's the rate, mass rate times the velocity. Kind of this nice, cute example. Any questions about the conveyor belt? The next one we're going to do is thrust. It's like a rocket experiment. It's very similar to this actually. So we're ejecting mass in the thrust problem, and you want to know the force that you get from ejecting mass from the rocket. Okay, let's do thrust. Conveyor belt example. Let's do thrust. Okay, so I need to draw another picture here. So yeah, we need a rocket. So we have a rocket. So that's a rocket. And it's moving at some velocity v. Rocket. But out of the back is some mass is coming out. So we have a rate that mass is coming out. And because, so what this is being pushed out of the rocket, and that mass has a certain momentum with it. And so the question is, what's the force on the rocket because of the exhaust of from coming out the back of the rocket? So the rocket feels gravity. So these are from gases coming out the back. So there's a relative velocity. So that's V gas minus V rocket. Is the velocity of the gases with respect to the rocket. So if it's coming out the same velocity as the rocket, it just stays with the rocket. You don't have anything to push off of. So you only get a thrust depending upon the size of the relative velocity. And so F thrust is equal to m dot, which is, so this is dm dt is equal to m dot times v rel. And that's the answer we're going to get. But in order to derive that, we'll think about momentum conservation in order to understand why that makes sense. In fact, so you can recognize this formula as being essentially the same as we had for the conveyor belt problem. It's the mass rate times the velocity. In this case, it's the relative velocity. Okay, so let's be a little bit careful. So that's the answer. And so you know that the momentum of this with the change in momentum of the rocket depends on the dm times velocity difference. So this makes sense, but it sometimes people get confused because when you write momentum, it's mv, and so if you do dp, you don't want to do dmv plus md. So this dm times v m times dv. So this is now confusing if you start taking derivatives. mv dot. You don't want to do that. You have to be really careful not to do that because that's not necessarily correct when you're trying to think of the total momentum that's conserved for the problem. So let's think about the total momentum in the at the moment. So we're gonna push out a small amount of mass dm. So let's look at the total momentum in the beginning. It's going to be m plus little m times v, where this is the velocity of the rocket. And then later on, it's going to be m times v rocket plus dv. So that's how much the rocket itself is changed, plus dm, which is how much, wait, this is a small mass, dm. So that's how much, how much is this guy changing? And so he's v rocket plus v rel. And this, so this is the momentum afterwards, this is the momentum before. They have to be the same thing. And so when you set these two to be equal, this and this term drops out, this term and this term and this term drops with that one, and that leaves you this term and this term. And so what you get is m dv plus dm v rel is equal to 0. And then if we divide both of these by dt, plus dm dt v rel is equal to 0, that gives us, so this is the mass of the rocket times its acceleration. So this is the force that's on the rocket, which I'm going to call the thrust, is got to equal this thing, which is dm dt times the relative velocity. And there's a minus sign here because the VREL is in that direction, so the force on the rocket is in the opposite direction. So you can ignore if we define VREL as negative, then you get the signs make sense. So this is consistent with where we wrote over here, which is what we expected. But we went through and decided, we started off with a certain momentum in the rocket plus this little bit of mass that we're ejecting. And then we used momentum conservation to find the thrust of the rocket. So there shouldn't be any ambiguity in the fact that this is the equation for the thrust. Okay, so I think we're out of time today. But the last thing to do, actually, you can now take into account, say, the mass change, you can solve for like velocity as a function of time if you want with the thrust equation, and taking into account the fact that the mass of the rocket might be decreasing during while it's being launched. And so that's what people do to try and predict trajectories for rockets. They assume a certain rate of burn for the fuel, and they assume a thrust for that burn rate. And then you predict the final mass and the final velocity of the rocket, and you try and make it so your rocket, actually gets where you want it to go, which might be in space, or maybe just will be up high for a certain length of time to come down. But you can solve these if you take into account solve the equation where you take into account the mass as a function of time and the velocity as a function of time. Okay, so any more questions? And we'll end there for thrust. Questions? Okay, I can't hear any questions, so otherwise I'll see everybody on Thursday in Hoyt. And hopefully we'll have a more functional recording and the mic will work better for those of you guys online. So see you everybody on Thursday then.
Thank you.
Thank you.
Thank you.